right now, your code thinks the word apple is closer to the word banana than it is to the word MacBook.
Which is pretty funny when you think about it.
Yeah, I mean, it doesn't actually know what a fruit is, right? It doesn't know what a computer is.
That at all.
It only knows that the mathematical distance between two specific coordinates in a massive, say, 124-dimensional space is 0.02.
Exactly. Just raw numbers.
Right. So welcome to the geometry of meaning. It is late. You've probably got your IDE open on one monitor, a blinking cursor waiting for you, and a cup of coffee that went cold about 2 hours ago.
Sounds about right for a Tuesday.
Yeah. You're a software engineer, and lately it just feels like every time you blink, there is some new AI framework or a new model architecture or some new paradigm you were supposed to master.
Oh, the noise out there in the developer community right now is just deafening.
It really is. But tonight, we are cutting through all that noise. We're doing a deep dive into some source notes on a concept called the geometry of meaning.
A really fascinating set of notes, by the way.
Truly. And our mission tonight is to completely demystify embeddings, because this is the foundational infrastructure layer, like the absolute bedrock data structure that allows an AI to actually process and categorize human language. Okay, let's unpack this.
Yeah, so we are starting at the very bottom of the stack here, long before any actual text generation happens.
Right, before the LLM even says a word.
Exactly. And the stakes here are profound because we are taking this abstract, highly subjective, incredibly messy concept of human language.
Very messy.
And we're forcing it into a strictly mathematical construct. I mean, if you want to understand how an AI processes a search query across a massive database or, evaluates a prompt, you have to understand the translation from raw text into floating point numbers.
It's basically the prerequisite to any optimization you're going to do. Spot on, because when I think of human meaning, I naturally picture like a web of associations or a knowledge graph.
Sure, yeah.
But the sources highlight that for a machine, embeddings are literal numerical arrays that map meaning into a high-dimensional geometric space. It's literal geometry.
Right. The core idea is that similar concepts get assigned arrays that place them close together in this physical space, while unrelated concepts are pushed far apart.
Yeah. They are mathematically repelled.
So if we imagine like a massive 3D map of a city, the coordinates aren't pointing to streets, they're pointing to words like dog or cat. And the physical route between them represents how closely related they are. What's fascinating here is how we actually calculate the relationships between those lists of floating point numbers.
Okay, how does it work?
Well, the system doesn't just look for exact string matches. It measures distance and direction. In code, this is typically done using cosine similarity or just a simple dot product.
Right. High school vector math.
Exactly. You are taking two vectors and calculating the literal angle between them in this geometric space. So if you have a vector representing the concept of front end and another one representing JavaScript,
the angle between those two vectors is going to be extremely narrow.
Yep. The cosine of that angle approaches 1. The system mathematically knows they are highly related.
And if you take front end and, database, the angle is wider, the cosine similarity drops, and the system knows they are further apart semantically.
I've got it.
But what's really striking in the notes is that the space also encodes directional relationships, not just, proximity.
Oh, this is the best part.
Right. Like, there's a classic NLP example about mapping the relationship between roles. If you calculate the mathematical vector, like the exact direction and distance from the coordinate for backend to database,
Right.
that specific directional vector represents a transition from application logic to data storage.
And you can apply that exact same directional vector elsewhere in the space.
Wait, literally the same math?
The exact same translation. If you start at the coordinate for front end and apply that same mathematical translation, you land geometrically right next to the concept of local storage or browser cache.
Oh, wow. That's wild.
It is. The embedding space hasn't just memorized a dictionary. It has mathematically modeled the structural relationship between architectural concepts.
So you are essentially doing vector algebra with concepts.
Precisely. Like moving from king to queen uses the exact same geometric path as moving from man to woman.
Okay, so the distance and direction are identical across parallel relationships. But that implies the compute required to map out the entire dictionary, to hold every single word and concept in this, perfect mathematical tension must be astronomical.
It's massive.
Because we can't just be calculating an XYZ axis for this. Which brings up the core architectural question here. How does an AI actually compile and organize this massive geometric map in the first place? I mean, it can't be a static mapping process.
No, not at all. The engine behind building this map is a process called contrastive learning.
Contrastive learning.
You start with random coordinates the model doesn't know anything at all.
Just noise.
Just noise. Then you feed it millions, sometimes billions, of examples of text. And the algorithm looks at pairs of text. When it sees tokens or concepts used in the exact same context, like deploying to production and shipping code, it calculates the error in their current geometric distance.
And then it physically updates the floating point numbers to pull their coordinates closer together.
Exactly. It adjusts the weights to narrow that gap.
Wait, so the training process is literally just a massive algorithmic game of tug of war.
That is a great way to put it, yeah.
But how does it organize millions of data points without the whole map collapsing into just a chaotic mess in the center? Like, to prevent all the coordinates from collapsing into a single dense point, it has to be pushing other things apart simultaneously, right?
It does.
So contrastive learning implies some kind of penalty. It's like, imagine organizing a terribly messy garage.
Okay, what we do?
You aren't just throwing items into binary keep or throwaway piles. You're refining the space through sheer volume.
Right. And the algorithm does this by utilizing what we call negative sampling.
Negative sampling.
Yeah. So for every positive pair it pulls together, it randomly samples unrelated concepts like deploying to production and baking a cake.
Right, completely unrelated.
Completely. And it actively updates their arrays to push them further apart.
So it's much more like a universe where connected concepts are attached by, like, invisible rubber bands pulling them together, while magnetic repulsions actively push the unrelated concepts apart.
That's a perfect analogy.
But doing that recalculation for billions of text pairs, I mean, how does the system reach a state of equilibrium without just oscillating wildly forever?
Well, the stability comes from the massive scale of the batch processing and the design of the loss function.
Okay.
When the system processes a huge batch of data, it calculates the contrastive loss, which is just a mathematical measure of how far all these rubber bands and magnets are from their ideal resting state.
So it's measuring the total tension in the system.
Exactly. It computes the gradient across the entire batch simultaneously and then updates the vectors in tiny, heavily penalized increments.
Tiny steps so it doesn't overshoot.
Right. And over billions of iterations across massive GPU clusters, the web of rubber bands and magnets snaps into a state of physical equilibrium. The entire semantic universe just stabilizes.
Man. But if you're recalculating millions of rubber band tensions, the sheer size of the arrays you're doing that math on becomes your primary bottleneck, right?
Oh, absolutely. Memory bandwidth is the real killer here.
Because you mentioned calculating angles in a geometric space. And, developers are completely comfortable working with multidimensional arrays and tensors, but the notes indicate modern embeddings typically use dimensionality ranges of 384, 768, or even 124 dimensions.
Yeah, that's standard for a lot of production models today.
So you have an array with 124 floating point numbers representing a single chunk of text.
Yes. And each of those 124 indices represents an axis of measurement, a latent feature of the language.
Like what?
Well, one axis might loosely correspond to the concept of formality, another to sentiment, maybe another to plurality.
Right.
But the vast majority of these axes represent abstract semantic features that humans don't even have words for.
It's just alien logic.
Pretty much. The neural network discovered them purely because they mathematically reduced that contrastive loss during training.
That's wild. Now, the numbers 384, 7668, and 124 obviously align with standard memory architectures and hardware optimization.
Powers of two and all that, yeah.
Right. But the actual range of dimensionality must be a deliberate choice, right? Like a trade-off about semantic resolution versus compute bloat.
It's the intrinsic complexity of human language dictating the architecture. I mean, think about it. If your array only had 10 dimensions, you wouldn't have enough axes to capture the subtle distinctions between a phrase like system crash and system slowdown.
Because there just isn't enough mathematical space to separate them.
Right. The vectors would be forced into the exact same coordinates.
Big overlap.
But on the other end, if you blow that out to, say, 100,000 dimensions, you hit what we call the curse of dimensionality.
Right, the curse of dimensionality.
You end up wasting massive amounts of compute capacity calculating spatial relationships across axes that just don't add any semantic value. The distances between all points start to look exactly the same. So 124 dimensions provides the necessary semantic resolution without completely crippling your compute.
But even at 1024 dimensions, we are talking about serious latency.
Oh, definitely.
Because if you are a software engineer building a search application and a user types a query, your system have to convert that query into a 1024 dimensional vector and then calculate the cosine similarity against millions of other 1024 dimensional vectors in your database just to find the nearest neighbor.
Yeah, doing that math at scale is incredibly computationally heavy.
And latency is the absolute enemy of a good user experience.
It is. The infrastructure required to run high-dimensional vector search at low latency is immense. You have to utilize complex indexing algorithms like hierarchical navigable small world graphs, HNSW, just to avoid scanning every single vector one by one.
Right, approximate nearest neighbor search.
Exactly. But even with optimized indexing, memory bandwidth becomes a massive bottleneck. And that is why the source material highlights a really brilliant recent architectural breakthrough called Matryoshka embeddings.
Okay, here's where it gets really interesting. Because the Matryoshka concept is literally a Russian nesting doll of data structures.
It really is.
The notes explain that if your application needs a faster query, you can just mathematically truncate the array, like literally slice off the outer layers of the doll, drop down to a smaller dimensional vector, and the similarity search still fundamentally works. You're telling me I can just chop the array in half and it doesn't break?
This raises an important question about the loss function during the initial model training.
Okay.
Normally, if you train a standard 1024 dimension model, the semantic weight is distributed somewhat equally across the entire array.
Right, it's all spread out.
So if you just truncate the last 500 floating point numbers to save memory bandwidth during a search, the geometry completely breaks. The vector points to absolute gibberish.
Because you just chopped off half the coordinate data, the angle shifts entirely.
Exactly. But Matryoshka embeddings modify the loss function during that contrastive learning phase we talked about earlier.
Yeah.
The algorithm is heavily penalized for errors in the first 64 dimensions.
Oh.
Yeah, forcing it to pack the most critical, foundational semantic context into the front of the array, the innermost doll.
That is so clever.
And then it's much more forgiving of errors in the outer dimensions, allowing the system to use indices 65 through 1024 to store the hyperspecific granular nuances.
So the first 64 numbers in the array hold the core, meaning like this text is about a server error.
Yep.
And the remaining numbers stretching out to 1024 add the nuance, like this is a timeout error occurring specifically on an Nginx reverse proxy during a high traffic spike.
You nailed it.
Yeah.
And the implications for system architecture are massive here. It allows for dynamic scaling of your search pipeline.
How so?
Well, if you are querying a database of millions of documents, you perform a lightning-fast, cheap initial nearest neighbor search using just the innermost 64 dimensions.
Ah, because the vectors are a fraction of the size.
Exactly. They fit perfectly into the ultra-fast cache of your hardware.
Right.
So you use that to quickly filter out 99% of the database.
And then you take the remaining 1% of candidate documents, the ones that are actually relevant, load up the full 1024 dimension arrays for just those specific documents, and do the computationally heavy cosine similarity calculation to find the exact perfect match.
Bingo. You get the latency of a tiny model with the semantic resolution of a massive one.
It solves the classic software engineering trade-off of latency versus accuracy purely through clever data structuring. I love that.
It's elegant.
It really is. Okay, so we have these highly optimized nested arrays. We understand the contrastive learning that sets their values, and we know how the dimensionality impacts compute. But let's look at the ultimate practical payoff for the listener who's actually, deploying this into a real-world application right now.
The fun stuff.
Exactly. The sources indicate the biggest payoff happens when you plug these embeddings into a RAG pipeline retrieval augmented generation.
Right, so RAG is basically how you give an LLM access to your private database.
When a user asks a question, you embed their prompt, use a vector database to retrieve the geometrically closest documents, and pass those documents to the LLM to generate an answer.
Which is pretty standard architecture now. And the notes point out that fine-tuning your embedding model on your specific domain-centric data is often the single highest impact engineering improvement you can make for production RG systems.
I have to push back on that, though.
Okay, weigh in on it.
Fine-tuning an embedding model, like actually recalculating all those weights and adjusting the coordinate space, is expensive, and it's computationally heavy.
It can be, yeah.
So if a 1024 dimension model already perfectly captures the intrinsic complexity of human language, why do I need to fine-tune it at all? Why wouldn't I just use a standard off-the-shelf embedding model perfectly fine for my search system to handle the retrieval and then just inject a domain-specific glossary directly into the LLM's system prompt.
It's a fair question.
Right, why go to the trouble and expense of shifting the actual geometric coordinate?
Well, prompt injecting a glossary is a super common workaround, but it fundamentally misunderstands the bottleneck in a RAG system.
Okay, why?
Because the LLM only sees the documents that the embedding model retrieves. If the initial geometric map is wrong, the vector database retrieved the wrong documents. The LLM never even sees the correct information, so your glossary in the prompt is completely useless.
Ah. The retrieval fails before the generation phase even begins.
Exactly. Let's look at a concrete architecture example. Imagine you are building a RAG tool for a hospital's intensive care unit.
Okay, high stakes.
Very. In a standard off-the-shelf embedding model trained on the general internet, the vector for the word monitor might be clustered geometrically near screen, display, or LCD.
Right, computer monitor?
But in an ICU, monitor means a heart rate tracker. It should be clustered geometrically near vitals, patient, and EKG.
Oh, I see. So the baseline mathematical map is completely accurate for the broader internet, but semantically broken for that specific database.
Exactly. If a doctor searches your RD system for patient monitor issues, the off-the-shelf embedding model calculates the vector for that prompt, finds the nearest neighbors based on its general map, and pulls up IT support documents for broken computer screens.
Which is completely useless to the doctor.
Worse than useless. But fine-tuning the embedding model on the hospital's specific data mathematically recalculates those arrays. It physically moves the coordinate for the word monitor away from the IT cluster and snaps it into the medical cluster.
And the same issue happens in software documentation, too.
Definitely.
If a user searches an off-the-shelf model for server issues, the system has to distinguish between a Linux backend server and, like, a restaurant waitstaff server.
Exactly. Fine-tuning is what turns a generalized mapping system into a true domain expert. You are recalculating the mathematical distances to reflect the actual reality of your specific business logic.
That makes a lot of sense.
And this highlights why you can't just rely on the LLM to sort it out at the end. Your finite context windows and high token costs. You cannot afford to retrieve 50 irrelevant IT documents, feed them all to the LLM, and ask it to find the medical data.
Right, that's just bad engineering.
It really is. Fine-tuning the embedding layer ensures that the top 3 results retrieved from your vector database are precisely the right context. The embedding is the foundation of the entire pipeline. If the underlying geometry is flawed, everything built on top of it collapses.
So what does this all mean?
Let's bring it home.
It means embeddings aren't just some abstract concept you can ignore while you focus entirely on the shiny LLM front end of your application.
Yep.
They are the crucial infrastructure layer. They give AI systems the fundamental mathematical ability to parse, to categorize, and to search through human language by translating it into a high-dimensional geometry of meaning.
Beautifully said.
And getting that geometry right through proper dimensionality choices, optimizing hardware caching with Matryoshka nesting, and fine-tuning the coordinate space for your specific domain that is the engineering work that separates a brittle prototype from a robust production-grade system.
That's the real work.
And this perfectly sets up where the source material is taking us next. Tomorrow, we step from this infrastructure layer into the world of multi-agent systems.
Oh, this is going to be good.
Because if embeddings give an individual model the ability to understand and search, multi-agent frameworks give them the ability to collaborate, delegate, and execute as autonomous teams.
As you get back to your code tonight, I want to leave you with one final thought to consider about system architecture.
All right, lay it on us.
We just spent all this time talking about how we force human language into floating point arrays so that an AI can understand us.
Right.
But as we move toward these multi-agent systems, specialized AI nodes, collaborating together at lightning speed, what happens when those agents recognize that routing communication through human language tokens is incredibly inefficient?
Oh, man.
What happens when these autonomous systems start dynamically compiling their own embedding spaces to pass data directly to each other? Plotting a geometry of meaning, a massive multidimensional map that doesn't correspond to human language at all.
A language of pure vectors.
Exactly, a geometry of meaning that we might not even be able to comprehend.
Now that is a thought that will keep you up staring at that blinking cursor. Until next time.